Something happened at the edge of the universe, and astronomers are still trying to figure out how to explain it to the public without sounding like they've lost their minds. Because right now, in laboratories and observatories across the world, scientists are staring at James Webb Space Telescope data that doesn't just raise questions. It raises alarms. For decades, we were told a clean, comforting story. The universe began in fire 13.8 billion years ago. For hundreds of millions of years afterward, it was dark, quiet, and empty. Slowly, gas clouds collapsed. Slowly, the first stars ignited. Slowly, galaxies stitched themselves together, one clumsy step at a time. That slow, patient timeline was the backbone of modern cosmology. It's in the textbooks, it's in the documentaries, it's the story every planetarium show has told for 50 years. James Webb was supposed to confirm that story in stunning detail. Instead, it's quietly dismantling it, one observation at a time. And 2026 has been the year it all came to a head. Let's start with what happened in January. A team of researchers at Texas A&M, digging through Webb's deepest infrared data, found something that should not have been possible. An ongoing merger event of at least 5 galaxies, crashing together roughly 800 million years after the Big Bang, and evidence that the collision was already scattering heavy elements far beyond the galaxies themselves. That might sound like technical jargon, but here's what it actually means. Galaxy collisions and the spreading of heavy elements like oxygen across space were things scientists assumed took over 1 billion years to even begin. Webb found it happening earlier, much earlier. As the researchers themselves put it, this discovery shows the universe was already interacting and enriching its surroundings with heavy elements far sooner than any model predicted. Phys.org, phys.org. That alone should have been the headline of the year. But Webb wasn't finished. In July, just weeks ago, an international team of astronomers announced they'd found something that, by every rule I thought we understood, simply shouldn't exist yet. A massive barred spiral galaxy, cataloged as M49 BSG Z5, spotted at a point less than 1.2 billion years after the Big Bang. A galaxy with organized spiral arms, a dense central bulge, and a bar of stars slicing through its core, funneling gas inward like a cosmic conveyor belt. Structures like this, with rotating disks cold and stable enough to hold a shape like that, were thought to take billions of years longer to form. According to the paper, this galaxy's large size, high star formation rate, and mature disk-like structure directly challenge existing models of when galaxy disks are supposed to settle into shape. JWST discovers a new barred spiral galaxy +2. Think about that for a second. This isn't a blurry smudge of gas. This is a fully organized spiral galaxy with a bar and a bulge sitting in a part of the universe that was supposed to still be in its cosmic infancy. It looks less like a newborn and more like a fully grown adult standing in a nursery. And it doesn't stop there. Just 3 days before this video, a team from Durham University published a discovery that pushed things even further. Using Webb's data, they identified what appears to be the most distant known nuclear disk ever detected inside a galaxy. Proof that complex galactic structures were already assembling far earlier in cosmic history than anyone expected. The nuclear disk isn't some loose, chaotic blob of gas. It's an organized structure at the very center of a galaxy, the kind of intricate architecture you'd expect from a galaxy that had billions of years to mature, not one still supposedly in its early formative stages. Phys.org. Then there's the giant galaxy that refuses to spin. Earlier this year, researchers using Webb found a massive galaxy from the early universe that, according to the study's lead author, showed no signs of rotation at all, a trait typically only seen in enormous mature galaxies much closer to us in time and space, a young galaxy behaving like an old one. Again, NASA science. Pattern. That's the word cosmologists keep circling back to, uncomfortably, in interview after interview. Not an isolated anomaly, not a single strange image, a pattern, merging galaxies too early, spiral structures too early, organized nuclear disks too early, giant galaxies behaving like ancient ones too early. Every single time Webb looks deeper into the past, it finds structure and complexity that, according to the standard model of cosmology, simply should not be there yet. And here's the part that should genuinely unsettle you. This isn't fringe speculation from some corner of the internet. This is coming from Nature Astronomy, from the Astrophysical Journal letters, from monthly notices of the Royal Astronomical Society. These are the most rigorously peer-reviewed journals in the entire field. The scientists behind these papers aren't chasing viral headlines. They're some of the most cautious, conservative voices in astrophysics. And even they are now openly stating, in their own published language, that the standard model of galaxy formation is being challenged in ways it wasn't built to survive. So the question isn't whether something strange is happening at the edge of the observable universe. Webb has already answered that. The real question the one that's about to get a lot stranger, is what these structures actually mean for the timeline of everything. Because in the next section, we're going deeper into the objects that don't just challenge galaxy formation. They challenge the very foundation the Big Bang model was built on. If section 1 left you uneasy, what Webb found next is the part that actually made theoretical physicists start arguing with each other in public. Because merging galaxies and spinning disks are one thing. But what astronomers found, scattered across Webb's deep field images, is something else entirely. Something so strange that scientists didn't even have a name for it at first. They just started calling them little red dots. That name sounds almost cute. It is not. Little red dots, or LRDs, are compact objects glowing across the early universe in far greater numbers than anyone expected to find. They have a strange, almost fingerprint-like light signature. Bright and ultraviolet and optical light, but with an unusual dip in between, plus broad emission lines that hint at something violent happening inside them. A study posted in May 2026 argues that these objects could be black holes caught in rare, violent bursts of feeding at a rate that exceeds theoretical limits, not just growing. Force-feeding themselves at a pace physics says shouldn't be survivable. Phys.org. Here's why that matters. One of the researchers behind a separate February 2026 study on these objects put it bluntly. Finding black holes this early in the universe goes directly against the standard model of how the universe builds structure, from small pieces up to big ones. We're not talking about a slow climb from stellar remnant to supermassive giant. We're talking about black holes appearing to skip the line entirely, showing up already monstrous when the universe had barely had time to cool. Arxiv. And scientists don't even agree on what these things actually are yet. That's the part that should really give you pause. This isn't a case of one confirmed answer being dramatic. It's a case of some of the most respected astrophysics teams on Earth, proposing wildly different explanations, all in the same year, because none of them can fully explain what Webb is showing. One team, working out of the University of Copenhagen's Cosmic Dawn Center, spent 2 years analyzing Webb's data and concluded these red dots are young black holes, 100 times less massive than previously believed, wrapped in a cocoon of gas they are devouring in order to grow, generating enormous heat that glows through the cocoon and gives the little red dots their distinctive color. Arxiv. But a competing team at Harvard and the Center for Astrophysics reached a strikingly different conclusion just months earlier. Their theory, these red dots aren't black holes wrapped in gas at all. There's something almost unimaginable. They're watching some of them being born in real time. Space.com. Read that again. 2 separate, highly credentialed research teams using the same telescope, looking at the same class of object, and arriving at 2 fundamentally different explanations. One says these are baby black holes gorging themselves at impossible speed. The other says we're witnessing the literal birth of a black hole from a collapsing supermassive star. And a third team even went so far as to confirm one specific object, nicknamed Glimpse 175, showed signs consistent with being what they called a black hole star, a ravenously feeding, growing, supermassive black hole cocooned inside a dense cloud of partially ionized gas. Arxiv. That's 3 theories, 3 teams, 3 different pictures of what's actually happening at the dawn of time. And none of them are fringe scientists. These are people publishing in the Astrophysical Journal, backed by institutions like Harvard, UT Austin, and the University of Copenhagen. So why does any of this matter beyond academic curiosity? Because among the most striking discoveries Webb has delivered are supermassive black holes, some reaching 100 million times the mass of our sun, showing up just a few, 100 million years after the Big Bang. That is not a small footnote. Under the timeline we were taught in school, black. Holes are supposed to start small, from the collapsed cores of massive stars, and slowly, patiently accumulate mass over billions of years. Webb is showing us monsters already fully grown at the starting line. Uric alert. And this isn't a one-off detection either. According to the researchers modeling this behavior, the glowing red dots Webb has already spotted are likely just the most visible fraction of a much larger hidden population, the most luminous examples of a much larger group of black holes in the same bursty growth phase, with many more remaining below what current instruments can even detect. In other words, what we're seeing isn't rare. It's the tip of something enormous. Phys.org. Put it together with everything from section 1, merging galaxies far earlier than expected, organized spiral structures far earlier than expected, giant galaxies that behave like ancient ones, and now add supermassive black holes appearing at a scale and a speed that breaks the standard model of black hole growth. This isn't one anomaly anymore. This is a full-blown pattern stacking up across every category of object Webb has looked at. And here's what should genuinely concern you as we head into the next section. If galaxies formed too fast and black holes grew too fast, then something in our fundamental timeline is off. Not by a small margin, not by a rounding error, by enough that entire theoretical frameworks are being rewritten in real time in papers being published this year, not decades from now. And in the next section, we're going to look at exactly what scientists think could be causing this. Because the leading explanations range from the early universe just worked differently than we assumed to something far stranger involving the very structure of the cosmos itself. So if the objects are real and the numbers hold up, what's actually causing this? This is where things get genuinely interesting. Because unlike the version of this story you'll find in the more sensational corners of the internet, the real answer isn't the Big Bang never happened. The real answer is messier, more scientific, and honestly, in some ways scarier, because it means the disagreement is happening at the highest levels of the field in real published papers right now. Let's start with the core problem in plain terms. Standard cosmological modeling, the Lambda-CDM model, the framework that has successfully predicted the large-scale structure of the universe for decades, sets a hard ceiling on how efficiently a young galaxy can convert its raw gas into stars. Researchers, analyzing Webb's earliest galaxy candidates, found that some of these systems would require a baryon-to-star conversion efficiency unphysically approaching, or even exceeding, 100% to explain their observed mass. In other words, for these galaxies to be exactly what they appear to be, they'd have to be turning every scrap of available gas into stars with zero waste, a feat the models say shouldn't be possible. If confirmed at those levels, researchers note this could signal genuinely new physics beyond standard structure formation. That's not a small statement. That's some of the most careful astrophysicists on the planet saying, in formal academic language, that the numbers don't currently add up. But here's where the story gets more careful than the version people love to post online. Scientists aren't panicking and throwing out the model. They're doing what scientists actually do, testing every possible mundane explanation before reaching for an exotic one. And there are several real candidates on the table. One explanation is observational. Some researchers argue the apparent tension could come down to how we're estimating stellar masses in the first place, differences in the assumed initial mass function of stars, calibration issues with Webb's own instruments, or the surveyed patches of sky simply being unusual outliers rather than representative samples. Another explanation points to contamination. Some of these ultramassive-looking galaxies might not be pure starlight at all. They could be partially powered by active galactic nuclei, feeding black holes whose glow gets mistaken for stellar mass, artificially inflating how massive the galaxy appears to be. Even brown dwarfs, cool substellar objects, have been floated as possible contaminants skewing early data. Then there's the more radical camp, the researchers willing to say maybe the universe itself needs new ingredients. One line of work proposes early dark energy, a version of dark energy that behaved differently in the extremely early universe before decaying away, potentially reshaping how quickly structure could form. Another proposes primordial black holes, formed before the first stars ever ignited, acting as gravitational seeds that let galaxies and quasars assemble far faster than gas collapse alone would allow. Others are testing whether dark matter itself might not be perfectly cold the way the standard model assumes, but instead warm, moving faster and clumping differently in ways that could naturally produce these fast, massive early structures. And in April of this year, a team out of UC Irvine published research directly targeting this exact controversy, arguing that once you properly combine statistical uncertainty with systematic observational effects, much of the impossible, early galaxy tension may resolve without needing new physics at all. Meanwhile, other 2026 papers reach the opposite conclusion, arguing that the tension holds up even after accounting for those uncertainties, and that something in the standard model genuinely needs revision. So, which is it? Honestly, right now, nobody knows for certain, and that's exactly why this story matters. This is not a solved mystery being sensationalized for clicks. This is an open, live scientific fight happening in real time, in real journals, between real research groups who disagree with each other. On one side, astronomers who believe better data and better statistics will eventually tame the anomaly. On the other, astronomers who believe we are staring at the first real observational crack in a cosmological model that has ruled unchallenged for over 20 years. And layered on top of all of this is a separate, equally uncomfortable puzzle astronomers already had before Webb ever launched. The Hubble tension, the stubborn disagreement between how fast the universe appears to be expanding based on the early cosmic microwave background versus how fast it appears to be expanding based on measurements of nearby galaxies. Multiple independent methods, megamaser galaxies, alternate stellar populations, even gravitational wave. Measurements from colliding neutron stars keep landing on the same higher expansion value, refusing to match the early universe prediction. If no hidden error turns up, that means something happened between the early universe and the one we live in, now that the standard model simply does not capture. Webb's early galaxy data is landing directly on top of that unresolved fracture at the worst possible time for anyone hoping for a clean answer. Put simply, cosmology currently has two open wounds, not one: a galaxy formation problem and an expansion rate problem, and nobody working in the field is confident they're unrelated. This is the part of the story most viral videos skip entirely, because scientists are testing 7 competing theories and don't fully agree yet. Doesn't sound as clean as physics is broken. But it's the more honest version, and honestly, it's more unsettling too, because it means we're not watching a mystery already being calmly explained away behind the scenes. We're watching it unfold live, with some of the smartest people in the field openly uncertain which side of this debate is going to win. In the final section, we're going to look at what leading scientists themselves are actually saying about all this, what it could mean if the new physics camp turns out to be right, and where this entire investigation goes from here. So where does all of this actually leave us? Not with a broken universe, not with the Big Bang erased, but with something almost more unsettling in its own quiet way. A live, unresolved argument at the very center of modern cosmology, playing out in real papers published this year by scientists who are not agreeing with each other. Let's hear directly from the people doing this work, because their own words carry more weight than any narration ever could. Volker Braun, a professor of astronomy at the University of Texas at Austin and co-author of research on these early black holes, put the core problem simply: finding black holes this early in cosmic history goes against the standard model of how the universe builds. Structure, from small pieces up to large ones. That's not hedging. That's one of the field's own respected voices, admitting the standard story doesn't currently fit what Webb is showing. Darach Watson, one of the lead researchers behind the Cosmic Dawn Center's 2-year study of the little red dots, described these objects as young black holes far less massive than previously assumed. Wrapped in gas, they're actively consuming to grow larger, generating the intense heat that gives them their strange color. And Kyle Finner, discussing the discovery of an unusually mature, massive galaxy cluster from a period cosmologists call cosmic noon, said something that sums up exactly where this field stands right now. It's still early in the JWST era, and if astronomers can gather data on tens or hundreds of similarly strange objects at this stage of the universe's history, they'll finally be able to put our cosmological models through a real test. Notice what none of these scientists are saying. None of them are declaring the universe had no beginning. None of them are declaring the Big Bang a myth. What they are saying, carefully and often, is that the tools we built to describe how galaxies and black holes form in the early universe are being stretched right up to their limits, and in some cases, possibly past them. That's a very different statement than physics is dead. But it is still one of the most important open questions in modern science, and here's the timeline that should genuinely put this in perspective. Webb has only been fully operational, delivering science-grade data since the summer of 2022. That means every single discovery covered in this video, the merging galaxy quintet from January, the barred spiral galaxy from July, the nuclear disk from just days ago, the ongoing little red dot debate, all of it happened within a window of less than 4 years of active observation. Webb is not a finished project revealing its final answers. It is a machine, still in its early operational years, and it has already forced multiple published peer-reviewed challenges to a cosmological model that stood largely unchallenged for over 2 decades. So what happens next? A few things are already in motion. Astronomers are actively pushing for wider field Webb surveys specifically, designed to gather larger, statistically robust samples of these early massive galaxies and little red dots, precisely because right now, much of the debate comes down to small sample sizes and measurement uncertainty. More data means these competing camps, the ones who believe better statistics will resolve the tension, and the ones who believe we're looking at a genuine crack in the model will finally get real answers instead of dueling papers. On top of that, NASA's Nancy Grace Roman Space Telescope, expected to launch later this decade, is being built specifically to survey far larger patches of sky than Webb can, which means it could either confirm that these strange, mature-looking early galaxies are common across the universe, or reveal that Webb happened to stumble into a handful of unusual outliers. Either answer is going to matter enormously. If wider surveys confirm what Webb has found so far, that early galaxies and early black holes really were forming faster, bigger, and more efficiently than any model predicted, then cosmologists will be facing one of the biggest structural revisions to galaxy formation theory in a generation. If, instead, better statistics smooth these anomalies away, then this becomes one of the more dramatic false alarms in modern astrophysics, a reminder of just how difficult it is to measure the very edge of observable time and space with total precision. But here's the thing worth sitting with as you close this video. Even in the most conservative, most cautious version of this story, the one where every anomaly eventually gets explained by more data and better statistics, something remarkable is still true. We built a machine capable of looking back far enough in time to catch our current best model of the universe struggling to keep up. That alone is one of the most extraordinary achievements in the history of science. Whether the Big Bang model survives this challenge fully intact, gets revised at the edges, or eventually requires a genuinely new ingredient we haven't discovered yet, the fact that we're even having this argument, backed by real data instead of speculation, means we are living through one of the most important windows in the entire history of cosmology. So here's the real question, the one actual scientists are still arguing over as you watch this. Do you think these anomalies get explained away as our instruments improve? Or do you think James Webb has found the first real evidence that our model of the early universe needs to be rebuilt? Type your answer in the comments, because this debate isn't settled, not even close, and there is nowhere better to keep following it than right here. If this video helped you actually understand what's happening at the edge of the universe, instead of just repeating the same tired clickbait claims you've probably seen elsewhere, subscribe, because Webb is nowhere close to finished, and neither are we.